Okay, so page 6 ready. We got some concepts. Now we'll still do just, basic math. If I double this, what happens to that? But I don't think we need our calculator necessarily for this first one. So we've got number 11 here on page 6. We've got 3 bugs on a record player, on a rotating record. Now, I should update this problem because I don't think, do y'all know what record players are? Someone last period said, oh, it's a CD. No, it's before CDs. They're much bigger. And just like a CD, you have to be careful where you touch. And if you scratch it, that's a bad thing. But records or LPs, I think that, is the cool way to call it. I think they're coming back. But anyway, records, it's a rotating platform. And so my demo up here, in a minute, I've got a horizontal platform and it can spin horizontally. Now this is one that has as little friction as you can. And so that's one reason we're going to use this one. But at the playground, merry-go-rounds are a rotating platform, right? Y'all know merry-go-rounds on the playground? Now, some people get confused. They're like, do you mean the carousel at Six Flags? Do merry-go-rounds have horses? Even Google disagrees. So tomato, tomato, at the end of the day, it's a horizontal platform rotating in a horizontal circle. Horses are not. But the merry-go-round that I grew up with, it had these bars you could hold on to. And you could actually move from the outer edge to the inner edge. And you felt different things. Yes? Has anyone ever been on this? What about the people in the center? So I got 2 Santas here. Okay. What about Santa here, or any person, bug, object, block, whatever you want to do? Santa in the middle, is he having fun? I mean, maybe he likes just spinning in a circle. Okay, maybe that doesn't make him sick. I don't know. But you can actually move to different positions. Now, yeah, slowing down. I spun it like a minute ago. But here, now Santa has a radius. And we learned last time Santa is going to trace a circle. What distance is that circle? Circumference, right? Circumference. And so depending on where you are, you have a different circumference, right? And we said circumference over period, the time for that circle is going to be different depending on where you are, yes? Okay. And so whether it's Santa on a platform, you on a merry-go-round, or 3 bugs on a rotating record, it's all the same thing, okay? And so let's work through number 11. By the way, I've heard, I haven't went to all 30 million parks in Allen, but I've heard from students over the years, no, my park doesn't have a merry-go-round. No, my park doesn't have. And I did Google it like years ago. You can thank the knuckleheads making bad decisions, like putting a motorcycle on a merry-go-round. Who does this? Knuckleheads, that's who. They ruin it for everybody. And so they've been deemed not safe. Now, I will tell you, down the road, close to here, is Spirit Park, the one that looks like an outdoor kind of, hideout. They have a merry-go-round, but it's been modified to have seats. And so you can't move inner to outer anymore, but you can sit and spin around. So you can't really move Santa on that one, but I guess it's technically a merry-go-round. Carousels at Six Flags, the one with the horses that I'm thinking about, it's the same thing, right? It's the same thing, except it has a horse. And so here, this is going to be a top view. Okay, because this rotating platform is on some tabletop. It's making a horizontal circle. So notice they don't tell us. We kind of have to dive into the problem and evaluate what we're looking at. And it says we have 3 bugs, 3 blocks, 3 Santas, 3 people, whatever, on a rotating record. Rank the following: period, speed, and acceleration. Okay, and speed, velocity, remember, you can have speed, magnitude, even if you're moving around in a circle and your direction's constantly changing, yes? So speed, if I accidentally say velocity, okay, I'm probably talking about the speed reference. And so notice what's different about, what's given that's different about the bugs. Their position. And when we talk about position in a circle, what reference point are we using? The center, because we want to talk about radius. Now, is that the exact center? I mean, I hope it's close. Get your ruler out, you can do some exact center, but there's going to be the center. And so the distance from their position to the center is what we would call the radius. Now, to me, the way it's drawn, maybe it's kind of hard to tell where B versus C, but who has let's rank all their radii. Who has the greatest radius? A. So the radius of A, who would be next? B. And if it's hard for you to tell, you can also use the outer edge of the circle as reference, right? The one with a greater radius has a smaller distance from the outer rim. And then C would have the smallest. So just that's our given. They give us radius. And so period, what equation, defining kind of equation that's not on the formula chart, are we going to use for period or that involves period? Do you remember? Right, so we had that speed, tangent speed, linear speed, whatever you want to call it there, circumference 2 pi r over period. So we know something about the radius. Do I know anything about the speed? And if you look ahead, that's the next thing we're ranking. So I actually can't use this equation. There's too many unknowns, right? At this point, maybe we use it later. Now, I know some of you are going to erase, but I like to show, I can't use it right now. I don't know the velocity to get a period answer. Here comes your new term. Well, it turns out period is independent of the velocity. And so for this, I'm going to use the rotating platform here. I got my Santa object, right? And so remind me of the definition of period. It's the time to make one revolution, right? And so now I am going to get this going. Harry Potter's not real, right? Now I'm not constantly pushing the platform. It's pretty frictionless. Can we basically say this rotation in a small window of time is constant? Work with me, yeah? Okay. And so I got Santa here in the center, no radius, right? Are they going to have any tangent velocity if you don't have a radius? And you're like, but they're spinning, right? But if you think about their center of mass, no, they're not moving, right? It just stays in the same point. Now your shoulder compared to your stomach, okay, maybe your shoulder, we're neglecting that right now, okay? But if we move Santa, maybe to half the radius, right? If I call the full thing radius, I give it an initial push. We see he makes a circle, right? And I could time it, like when he faces me, time, right? And so if I was really keeping time, I could get a number for the period. Or I can time 5 circles and then do a proportion to get the time for one, yes? Hint, hint on the lab next time. 1 circle might be hard, but can you get the time of 6 circles? Or 5 circles, 10 circles, and then do a proportion? Sure. Okay, well, let's get our Santa 2.0. By the way, it just so happens I have 2 identical Santas. Same, right? Mass same, base same. What if they are side by side, not on the center, so they both have a radius and they're side by side. And so again, if I time their periods, who's going to have a bigger period? The one with a small radius or the one with a big radius? Think about it. Make a prediction. Who's going to have a greater period? Small radius, big radius. Here we go. In 3. And here, I'll just put my hand for where they start, okay? So whoever reaches my hand first has the greatest, or shortest period actually, right? They would win the race. However you want to answer it. Here we go. In 3, 2, 1. Uh-oh. What are we noticing? It's the same. So as long as both Santas have enough grip to stay on, I'll do that demo here in a second, okay? Then they rotate, they sweep one circle, they sweep 360 degrees, or what's another way instead of degrees? How can you report one circle? In radians. One circle is how many radians? 2 pi radians in the same amount of time. Does it matter where they are? Does it matter the radius? No. And so this first part, I'm going to define a new term. This is a Greek symbol. You don't have to know the Greek, but it's omega, okay, and it is on the formula chart as angular speed, also known as angular velocity, also known as angular frequency. Why do you have 3 stinking, it depends what book you read, okay? So your formula chart says angular speed. I'm sorry, I may accidentally call it angular velocity as well. Angular velocity, how fast are you turning that circle? Okay, how fast do you sweep 360 degrees? So based on one full circle is 2 pi divided by period, okay? The unit for angular velocity is what? 2 pi, what's the unit for 2 pi? You said it earlier. Radians, not radius, be careful. No radius in this one. So radians per, what's our unit for period? Seconds. And so recognizing that it doesn't matter where your bug is, assuming they all have grip to stay on the platform, which unless told otherwise, I think is a safe assumption, they'll all have the same angular speed. And if you just identify one circle, well, that can be the same for both. And so what is the period? And you saw it with the 2 Santas. Who has a greater period? Neither. And so our answer to the first question is same, all equal, okay? And so period is all the same. Or you could say A equals B equals C, however, if that makes you feel better. All same. Good there? Okay. Velocity. And so I'm going to go on and highlight that new equation. And let's go on a scavenger hunt. And yes, it is on the formula chart. They don't solve it for omega, but look in the second column at the bottom of your formula chart. You'll see T equals 2 pi over angular speed. Same? Yeah, they just cross multiply switch. I don't know why AP solves it for T, because to me, as a definition, defining equation, it makes more sense this way. But tomato, tomato, it's there. That one is on the formula chart. Okay, VT, tangent velocity, or that speed. Hey, now that we know something about the period and the radius, can't we use the equation that we wrote down before? And so now looking at velocity or speed as 2 pi r circumference over period. Oh, wait a second. Looky, look. By the way, this is just a little thing you can do. If you haven't noticed, physics, we have a lot of equations. Sometimes we combine equations. What did we just define as 2 pi over period? Angular speed, we get a new equation. Velocity can also equal omega times r. Angular speed times radius. I don't know who, oh, ADT, that's security people, right? I don't know. Maybe they want to offer me free security, you think? No. Okay, so omega r, it's a new equation that we can use to figure out velocity. And so here we know the angular speed is the same for each. And so whoever has the greater radius, well, it's a direct relationship with speed. And so who's got the greater radius, greater speed? A. So it'd be A is greater than B is greater than C. Okay. And then the last ranking there at the top, AC. What's our equation for AC? Our new one, it is on the formula chart. Right, V squared divided by R. Now, if greater radius, greater velocity, does that mean greater over greater nets out? Is it all the same? It may be hard to tell, okay? Correct answer is there's a square in the numerator, but let me show you, again, physics, we like combining those equations. Can we put, since all we know is radius, and we already came to the conclusion about angular speed, can we write an equation in terms of angular speed and radius? So follow along. We're going to do some deriving here. Okay. What is V? We just said it's 2 pi r over t. Now, as a full numerator, it all gets squared divided by r. Well, 2 squared is what? If I square everything in the numerator, 2 squared is 4. Pi squared is just pi squared times r squared over t squared all over r. What's going to happen? R squared over r. One set cancels. So here's a derived equation for acceleration, centripetal. 4 pi squared times r over t squared. Not quite done. It's not in terms of omega, but this could be useful. We do know that they have the same period, and 2 pi is the same. It's a constant, or 4 pi squared is a constant. And so hopefully you see that whoever has the greatest radius has the greatest acceleration. But let's use that new equation. Remember, omega is equal to 2 pi over t. Well, what if I have 4 pi squared over t squared? What can we plug in for this piece? Omega squared times r equals your centripetal acceleration. Okay? And so when would you use these derived equations? For this rotating platform with multiple objects, they all have the same angular speed. So whenever you have same angular speed, same period, these equations can kind of be a shortcut. It looks a little easier to use, right? Or use the other one, the 4 pi squared r over t squared. Or just recognize that AC is directly related to r. And so the biggest acceleration is the one with the biggest radius. And so what was it, A, B, C? Good with the new equation, the derivations. You didn't have to go that far, but I did because I wanted you to see it at least once. And our answers to the rotating platform. All right, let's do the problem down below. Now, although it's on the same page, this one's not, it's a ball on a string. We got different masses, different lengths, different speeds. This is not a rotating platform. So don't start thinking, oh, they must all have the same angular speed, same period, okay? They're not. And so are we given radius? They give us length. If you were to imagine all of these making a circle, which is the assumption, is the length equal to the radius? Yeah, okay, we'll assume they're vertical circles, so 2L will equal the radius. L and 3L are the radius. Rank from greatest to smallest the following: period, centripetal acceleration, and net centripetal force. And so let's do period first. And so period, we said our new equation on the formula chart, it's going to look a little different, cross multiply, switch. It's that 2 pi over omega. Do we know omega? Are they on the same platform? Do they all have the same angular speed? No, I can't assume that. They might, but no, I can't assume that. And so we're not going to use this equation. Okay, plan A doesn't work, try plan B. So what other equation involves period? Well, V equaled circumference. I know something about R, divided by period. And period is what I'm looking for. They gave me something about V. So I know 2 out of 3 variables. This one, I just want to rearrange. And so I can cross multiply, switch. Period will be your circumference over speed. And so let's actually use the proportions that they give us. Okay, they don't give us meters per second or kilograms or meters, but they give us the proportion factor. And so the period of A, let's see, 2 pi is going to be the same for everybody. So it really just depends on that ratio of R to V. And so the R radius of A is a factor of 2. And the velocity factor is also a 2. So 2 over 2 is 1. Let's repeat with B and C. The period of B, well, we've got a radius of 1L, so 1, and a velocity of 1V, or 1, which is also 1. And then for C, again, it's radius to velocity, 3L to 2V. So 3 over 2 is 1.5. And so now we can rank who's the greatest period, who takes the longest to make one circle. C is greater than, well, A equals B. What if they wanted to rank angular speed? Who would have the greatest angular speed? Look at the equation we crossed out. What kind of relationship does period have with angular speed? The one with the greatest speed would take more time or less time? Less time. And so I'm just adding it because we can. If they wanted to rank omega and T have an inverse or indirect relationship. And so the one with the greatest omega or angular speed would take the least amount of time. So your ranking would not be C is greater. It would be A and B are greater than C. Feel okay? Okay. Now AC. What's AC's equation? What's the working equation we probably want to start with? The one on the formula chart. V squared over R. And so on this one, we are given some of the V's, we are given some of the R's or L's, right? And so we can just do with the given, do that ratio of V to R, not R to V, but we probably also want to remember to square V. And so for the acceleration of A, it has a velocity factor of 2, don't forget to square, divided by a radius factor of 2. 2 squared over 2 is 2. What about the acceleration of example B? Well, we'd have a velocity factor of 1 squared over a radius factor of 1. So 1. And then for C, example C, it has a velocity factor of 2 again. So 2 squared divided by a radius factor of 3. So that's 4/3 or 1.33. So to rank, the acceleration would be A is greater than C, greater than B. Everyone good? F net C. F net equals MA C, which we just found. And if they all had equal mass, then it would be the exact same ranking. Do they have equal mass? No. And so I'm going to use the numbers that we had from above and then use the mass factor value in the given. And so the net force of A would be what? Mass factor of 1 times 2. For B, it has a mass factor of 2 and an acceleration of 1. And C has a mass factor of 3 times 1.33, which is 4. And so we'd get C is greater than A equals B. So doing some algebra without actual values for the numbers, right? Those proportions, the factor of. Good deal? Okay. So that's page 6. Ask me questions before we move on to page 7. What do you got? Angular speed, the new piece, all that deriving with our older equations. Yes. Yes, the angle that it turns. And so whenever we do 2 pi, we're assuming 1 full circle. But does it have to be a full circle? No, maybe it only goes half a circle and you would use what radians? Half a circle would be 1 pi. And you would need to make sure you're consistent and only use the time of that half circle. You don't want to use the time of a full circle and the radians for half a circle. Just be consistent, right? Half, half, whole, whole. Maybe 3 circles. Maybe you know the time of 3 circles. You would do the radians of 3 circles, 6 pi. Okay. Page 7 is actually a callback to the video from last class with the loop-de-loop. And again, don't try this at home. Don't take a car and do a loop-de-loop. Stick to the roller coasters, right? Or spin water in a bucket. Did anyone go home and put water in a bucket? Oh, you're waiting for the weekend, huh? To do that physics experiment. Put water in a bucket and find that sweet spot, right? Okay. A roller coaster. And that's the car. There's not a car on here, but we'll say it starts on the left and we'll make it go to the right. A roller coaster has a mass m, factor of 1, and it follows a track at a constant speed. Now this is probably not real life. Is your roller coaster going to go on these loop-de-loops and be constant speed? How thrilling would that roller coaster be to never change speed? I mean, if you hate roller coasters, maybe it's good, but most roller coasters, it's all about the change. That's the thrill, right? You speed up, you slow down, you turn a corner, you don't turn, you know? And so this isn't necessarily real life for our loop-de-loops. And if you're thinking of the shock wave at Six Flags, it has 2 loops consecutive like this, but they're equal radius, FYI. It says the car is going to go on the inside of both loops. In other words, when you're at the top of the track, is it like the car on the hill that we did last time? If you're on the inside, you're going to go upside down, right? And so when you're at the top of the track, I know that the dots are above, that's just word being crazy, but you're actually upside down in the loop. And it tells us the second loop is twice the size of the first one. Now, is that diameter? Is that radius? It actually doesn't matter, because if you have twice the diameter, then you have twice the radius, right? And so I'm just going to write that out. The radius of the big loop is twice the radius of the small loop. Or if you want to go loop 1, loop 2, you could do that. Rank from greatest to smallest, that's just the norm, the following. A, the magnitude of the roller coaster's acceleration at points A, B, C in the small loop. D, not in any loop. And then E, in the bigger loop. D, as in dog, that's our old linear motion, right? When the car is at D, okay, it's done with the first loop, it's on its way to the second loop. Do you have centripetal acceleration at D? No. What would the linear acceleration be as you pass through D? Why 0? Right, it's 0 because don't forget, this one is special. They said this roller coaster is constant speed. And in a straight line, that would also mean constant velocity. And that would mean 0 acceleration in linear direction. But constant speed in your loop, you're going to have acceleration. And so I'll go in and tell you D is last, okay? And so we'll have something, 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 something greater than D. And I'm just going to make note it's equal to 0. Now, the only ones left are in circular motion. And so acceleration for a circular motion is that V squared over R. Constant speed, that's all the same no matter where you are. And so it's really dependent on radius. And so what relationship does acceleration have with the radius of the circle? Inverse, indirect. And so A and R are that inverse relationship. So who has the greatest acceleration? It would be the smallest radius, which is which points? A, B, C. And again, if you have constant speed, then they'd all be the same. So A equals B equals C. Greater than, and then your bigger the radius, the smaller the acceleration. E would come next. And again, D is 0. Let me take it one step further. Notice in the equation, and we did this day 1. So maybe think back to day 1 or page 1. A and R, there's no squares, there's no square roots. So we made a statement up above that the big circle had twice the radius. Could we make a statement about the acceleration? The bigger the radius, the smaller the acceleration. How much smaller? If it's twice the radius, it would have half the acceleration. So the acceleration of the big would be half the acceleration of the small. And if you don't like that fraction, you could move the 2 to the other side. You could say twice the acceleration of the big is the acceleration of the small. It's the same thing. As long as you know that the smaller circle has not just a bigger acceleration, it's got twice the acceleration. And we're going to use that fact later, okay? All right, what about B? Normal force. Remember, this is the force. If you remember the video from last time, he said when he was at the top of the loop, and it happened really quick. So he maybe didn't say top of the loop, but he's like, I felt weightless, right? Are we really weightless? Did we lose weight? No, you keep your weight, but right now you feel your weight because I push on the ground pushes on me. The ground pushing on me is normal force, right? Ride an elevator, ride the gravitron. When normal force increases, you feel heavier. That part of the roller coaster where you're like, oh, I feel like I'm being pushed into the seat. It's because the seat's pushing back on you more. Because again, you're trying to leave maybe that direction, okay? And so A, B, C, omit D, because we're just looking at the circular motion ones. And so rank the normal forces for the loops. That's what we're doing here. And so maybe we should draw some force diagrams. What do you think? Let's draw some quick diagrams. What about at A? If the cart is at A, what forces are acting on the cart? Normal force and gravity. And I'm going to kind of keep it calm so it's not too congested here. And so I'm going to go with calm, FG. And isn't gravity going to be the same all over? Okay. FG is the same at all locations. FN is not going to be the same. At A, the first point, normal force is pointing towards the center. Is it going to be equal, less than, or greater than the weight? Greater. Why greater? Right, to have centripetal force, to have circular motion, your center seeking force, whatever it is, has to be bigger than center opposing. And so Fn has to be bigger than the weight at A. Now circle around, I guess technically C would come next, right? What direction would the normal force be at the top of the loop? It would be down. Remember, this is the one where you're upside down. And so normal force, the surface is above you. And so it's pushing you down. Does it have to push you towards the center as much? I mean, gravity already is. Do you need help towards the center? No. And this is the part where you feel weightless. And so maybe it's just teeny tiny. Hopefully you can see that one. Teeny tiny, tip to tail if they're the same direction. And so normal force, you don't need as much help towards the center, so it's going to be smaller. Yes. So it depends on your speed. Question is, do you need normal force at the top? If you're at that minimum speed, special case, like we did last time, right? Water in the bucket, all that, weightless, there wouldn't be any normal force. But you could have some. It depends on the speed. And so we're just going to assume we're not at that special minimum speed right now. Okay. But yeah, it could reduce to 0. And then what about at B, the side? What direction is the normal force towards the center? And does it need to be as big? There's nothing center opposing. And remember, gravity is not center opposing here. And so it doesn't need to be as big as A. And if you notice, we're kind of ranking as we go. And so how do you feel when you ride this roller coaster? You'll feel the pressure into the seat the most at the bottom. Where do you have a possibility of feeling weightless? At the top, the middle, somewhere in between. Good deal? And so I'm going to go and write that. A is greater than B is greater than C. We know that from the small loop. Now we need to figure out, well, how does the big loop top compare? Okay. And so if we look, C and E are both at the top. Won't normal force still be down at E? But to compare the normal force on each, maybe an F-net statement, because the weight is the same. Weight is the same. Let's do an F-net statement just for the top, okay? So this is for C and E. And so sum the center-seeking forces. It's going to be gravity and normal force. And we're doing this to find something out about normal force. So maybe I isolate normal by subtracting the weight to the other side. And so Fn would be F net C minus Fg. And then to figure out, is it small loop, big loop that has the bigger normal force? Remember, Fg is going to be the same. So it doesn't matter which loop you're on, you'll always be subtracting the same weight. So really, whoever has the bigger normal force is going to have the bigger force in the beginning before you subtract, right? Who has the bigger centripetal force? Well, let's see. MAC, mv squared over r. Mass is the same, going around in the circle. V, speed, what did they say about speed? It's constant, and so this top part is all the same. And so who's got the greater centripetal force, the big radius or small radius? What relationship does net force have with radius? Say again. 1 over r. And so the one with the bigger net force, remember that's what we're trying to figure out, is going to have the smaller radius. And so the normal force of C should be greater than the normal force of E. Okay. And so where are we going to put E in the ranking? Well, it would be there at the end, okay? And D is omitted, mainly because the other locations, add or subtract your weight. This one, it's equal to the weight. I mean, we could throw it in there, but the focus was the loop ones, okay? Okay, now assume, here you go, that you barely make it around the bigger loop, not just both loops, because that's not possible. You barely make it around the top bigger loop, okay? And so I already gave it away. We're looking at the top and of the second loop. And so what's your normal force at the top of the second loop if you barely make it around? 0. So Fn at E is going to be 0. That's what they're telling us. And so what is the centripetal acceleration on the bigger loop? And remember that inverse relationship. We'll use that inverse relationship to get the centripetal acceleration on the smaller loop. And so look at part E or scenario dot E. We've got that F net statement we already wrote, and it was Fn plus Fg. But now knowing that you barely make it around, Fn minimizes to 0. F net equals MAC, AC equals V squared over R. On the right-hand side, FG equals mg. Notice what happens. Mass cancels. And so, oh wait, I took it too far. They wanted acceleration, didn't they? I took it too far. So I'm gonna, my next statement, I'm gonna go back to acceleration equals, hey, look at that. It equals G. I'm in free fall for the moment. And what did the guy say he felt? He felt like he was coming out of his seat. Free fall at the top at point E. And it's just for a semi-second. You may not notice it unless you're, doing it for the 5th time, really trying to be specific. If you were sitting on a bathroom scale, I know it's weird. If you're sitting on a bathroom scale, what would the scale read when you're at the top? It would read 0 because the scale is giving us the normal force. Well, if I'm just barely coasting over the top of the arc, I'm not pushing on the scale's not pushing on me. Normal force 0, right? Weightless. But I'm not really weightless. Okay, what about the smaller loop? Now, what did we say at the very top? We said the acceleration at the big loop is half the acceleration at the small, or we said that 2 times the acceleration of the big equals the small, and now they want the acceleration of the small, and so I can use that same. And so now we know the acceleration of the big is equal, for the moment, to 9.8 or 10 or g. And so acceleration of the small is going to be twice that. You're going to feel more g-force the tighter the loop is, the smaller the loop is, okay? Big loops, it should be okay, no g-force, okay? If you think about those planes, they're going to feel it the sharper the turn. Questions on page 7. Loop-de-loop. Okay, let's move on. Now, Davallo, this is that 50 years ago. That's the loop-de-loop original Daredevil Davallo or whatever, Allo Diavallo, I'm not sure. It was part of a circus performance. He rode a bicycle. And from the picture, you can see he used a ramp to gain his speed, right? No motor, okay? But go on and give this one, I'm going to put independent practice. If we have time another day, we can come back to it. But the rest of class, I want to give time for, and we're going to skip, Gravitron, page 14. So what am I skipping? Davallo, and then some of those tipper concept pages. So those are good for, like single concepts at a time. Now this was actually an old AP Physics B question. We modified it for Texas, I guess, right? And so it is at the state fair. I don't know. I haven't been in many years. Me and big crowds, not so much. But the Gravitron, Acceleratron, whatever it's called, Tex attends the local state fair, and he's attracted by the ride Acceleratron. After paying 6 tickets, who cares? Tex is invited to board the cylindrically shaped ride. So there's cylindrical. Look at the picture. Doesn't the circle look like an ellipse? It's a 3-dimensional picture on a 2-dimensional paper, right? But note to self, Tex is going to move around in a horizontal circle. This is a side view, and so it appears to be elliptical. And he's told to stand on the inner wall. That's what I told you. You saw the video. Oddly, there's no seat belts or safety harness. The fun starts when the ride begins to spin along the vertical axis. And you can see that vertical axis goes through the middle of the room. Once it reached a sufficient Goldilocks magical speed, rotational speed, the floor drops out from under his feet, or like in the video, the seat, the back that you're on, rolls up. In other words, your feet are no longer touching the floor, but you stay glued to the wall. Are you really glued? No. Draw a free body diagram for Tex on the diagram that below that reflects the forces acting on him when he's at this position pictured above. And so he's on the left side of that circle. What forces are acting on Tex? Gravity, still trying to pull Tex down. Your back's on the wall. There's a normal force. Ooh, it's a little different though. If your feet aren't touching the floor, but your back is on a vertical wall, what direction is the wall pushing on you? Horizontal, right? Normal force is perpendicular to the surface, perpendicular to the vertical wall is a horizontal normal force. Okay. And then it becomes a little, let's think differently. Y'all ready? You're glued to the wall, the floor is gone. How come you don't fall down? There's got to be this upward force that's equal and opposite to the weight. And it may not be evident because this is so special and different. What force is causing you not to fall down? It's friction. And I like that you said static because he's not moving. The ride is moving, but he's glued to the wall. It's gripping friction, right? It's static friction. And so that's what makes this one a little weird. Have we ever drawn friction up? Now we've drawn normal force kind of tilted with ramps. Maybe this is the first time or only second time it's gone horizontal. But this is a different kind of diagram, right? And so the frictional force is going to be the one balancing your weight. Newton's first law, balance on a single object, first law. What about Fn? Nothing balances Fn. But if you imagine the ellipse, the circle here, what direction is the normal force pushing on the person? Towards the center. And so we get F net C is going to be because of normal force. And this should answer the question, if this force wasn't there, you wouldn't make the circle. Imagine riding this ride without the wall. Would there be anything to push you towards the center? Well, I'd hope they have a rope then, right? And I could depend on tension, right? Okay, but for this ride in particular, you want the wall. It's going to help you stay in a circle. Good deal on the newish physics? New, not new? New look, but old physics. Okay, yes, go ahead. Good question. So frictional force can't ever go beyond your weight. And remember, static friction, it grows to a maximum, right? And so you don't have to be at the maximum to have static friction. It's not one set number. Remember, 2 finger, 4 finger, 6 finger, 8. Your maximum might be 8, but for Newton's first law to work, friction kind of reacts to what it needs to be. And it needs to be your weight in order to balance you. But yeah, as it spins faster, 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 normal force does increase. That's a true statement. Okay, and that's actually coming up. As the rotational rate, rotational rate, the rate at which you rotate. What are they really talking about here? Angular speed or velocity, okay? And so whether it's, by the way, in the future, maybe they give us RPMs, revolutions per minute, and we'll have to convert it to radians per second. That's coming in the spring. But as the rate of the ride spins faster, 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 it increases. What happens to the normal force? Now, I just gave the answer away, but let's look at the explanation. And so I'm going to continue that F net C. Now, previously, we spent time with omega, angular speed, when it came to velocity and acceleration. Put it in terms of force. And so F net C equals MAC, which is equal to MV squared over R. Yes? And we derived it once, so I'm not going to derive it again. It does take a while, but hopefully you remember I showed you that V would equal omega R. Remember I did that? 2 pi over T is omega. So omega is 2 pi over T. And so we can plug in omega r and all squared. And what does that turn into? Well, I get m omega squared. And then I get r squared over r. One set of r's cancels. And I'm left with normal force here is equal to m omega squared r. And so as you ride this ride, is your mass changing? No, mass is going to be constant. What about r? It's not like the bugs and Santa and the merry-go-round. You're not moving on the platform. You're stuck to the wall, so radius is going to be constant. And so what kind of relationship does normal force have with omega? When omega increases, normal force will increase. And you'll feel that. You feel it on any normal roller coaster. The faster it goes, the more you feel pressure with the seat. Okay? Same thing here. And so normal force increases. Now with this proportion, normal force is proportional not just to angular speed, but the square of the speed. That's what we're going to use to graph. It says sketch the normal force on text as a function of its speed. Oh, wait a second. Now it's giving meters per second. We're back to V. So maybe I go back to mv squared over r equals Fn. Okay. And so again, mass and radius are going to be the same. And so similar, but still a little different. Normal force varies with V to the square of V. Let F be the normal force when the speed is V. And so notice our axes. It's in terms of 0.25, 0.5, 0.75. Someone grab a calculator, be ready. Let's start with zero velocity. When this gravitron ride is not moving, is there a normal force to push you to the center? There's normal force with the floor, but in terms of pushing you to the center, if you're not moving, there's no need to push you to the center, right? And so we're making sense of a 0, 0. Okay? Don't just do it, assuming it's 0, 0. Make sense of it, okay? If you're not moving, nothing's pushing you to the center. What about, let's do a couple others. What about at the other end? What if I have a velocity of 1? Well, 1 squared is what force factor? 1. And so 1 force, 1 velocity, right about there. At this point, with 2 data points, should I grab a ruler and connect the dots? No, no, no. You need several dots. So maybe the next one we do, the one that's not too hard, what if we look at the 0.5V? 0.5V doesn't mean 0.5N. What are you going to do to your velocity? Square it. So what's 0.5 squared? 0.25. And so now I'm going to put my next dot right there. Now, hopefully you're like, well, it's V squared and Fn. So how do I connect these points? It should be a curved line, but I'm going to go on and tell you under the pressure of taking a test, AP exam, whatever, under all this pressure, some students are going to grab their ID, grab a ruler, and put it in between all those dots and draw a straight line. Wrong. How do we clearly see this is not a straight line? Will you shut that door? Okay. Let's do another data point. Someone be calculator ready. What if our velocity is 0.25? Well, let's square it. What's the factor of your normal force if you have 1/4 the velocity? 0.06, right? Is that what you said? 0.06 something. And so where do we see that on the graph? Ooh, that's harder. Let's see. Half of this would be 0.125, and then half-ish. And so here we would be closer to right there. Doesn't it look more parabolic at this point? Yeah, okay. So maybe you go ahead and draw it in, but I'm going to go ahead. It's not too hard. Let's do one more. 0.75 velocity squared would be what factor of normal force? 0.56. And so again, a little over the 5. Maybe, oh, it's doing it again. I can't remember how to correct this. Dang it. Stop it. Okay, well, hopefully you see where to put that other dot. Mine's not, oh, there we go. So point a little over. So now that should look like, oh, I better erase that straight line that I drew, right? And paper people, I hope you have pencil. Graphs, highly recommend pencil, okay? And so if I come in, do not just connect the dots, right? And so I would do a light, not that I'm trying to be artistic, but you want to fit a good trend, okay? And if you are in pencil, and if you're like, oh, but it says use pen. By the way, on the physics exam, you can use pencil. Make sure your markings are dark enough, but you can trace over that with pen at the end if you're worried about it fading. And so we get this parabolic relationship. Let's review. How would I linearize this? What would you plot to get a linear graph? Linear graph? What would I plot? I think I heard someone answer, but I wasn't listening, sorry. V squared. If I had V squared on the x-axis and V, then you would get a straight line, right? You got to look at the equation. We found that, ooh, let's keep it going. Oh, this is good. Okay, so we said Fn was equal to mv squared over r. And we said m over r never changed. Y'all remember linearization, right? Y equals, now be careful with the m, that's a slope m. What would your slope represent if you plotted v squared and f? Linear graphs have a constant slope. It would represent whatever's constant in your lab or experiment. So your slope would equal mass over radius. And I'm only writing the words because m, I don't want it confused. Okay. Little review of linearization. Okay. Why doesn't text slide down the wall? We've already answered this because why? Static friction. So static friction, okay, holds him up. Okay, just for time purposes, I'm not going to do the backside. I really, really want to, and so maybe next time we do. The key's already on Canvas. I've already went over the equations. The setup is there. I just haven't put it all together. But F, that's deriving the equation in terms of what they list, okay? And so I have fingers crossed I can do it next time. But I want to introduce Tetherball. And y'all, Tetherball is not any harder than what we've already done. And so the Tetherball analysis is written out here on page 16. But let's actually move to page 15, and we're going to do number 15, okay? Page 17, number 15. The top part is really just a concept. Not that it's bad, but we're going to address it in this problem. So here, let me get my astronaut back out. Ball on a string, tetherball. And so here is what we've done. We did a horizontal circle at a good speed. Maybe you're like, I don't see an angle. Maybe it's so small, you can't even tell there's an angle, right? But if I let it slow down, still a horizontal circle, but do you see the angle with the axis? Now it's rotating about a vertical axis, right? And if you've ever played tetherball, it wants to be straight up and down, right? Against the pole. And so a lot of times your angle is measured, like the picture shows, from the vertical axis. And so this is what we're looking at here. It's just moving in a horizontal circle, just like our text, gravitron. But instead of a normal force pulling to the center, what's pulling this astronaut towards the center? Tension, and more specifically, a component of tension, right? What's balancing your weight of the astronaut? Not friction. Vertical component of tension, okay? So it's not any revolutionary new idea, it's just a different application. And so we've got a mass that's swung by a string in a horizontal circle at some angular speed omega. As a result, the rope makes an angle theta with the vertical, like the picture. If the mass is 4 kilograms, the length is 2 meters, and theta is 30 degrees, what's the tension force? What's the angular speed? And what's the linear speed? Well, first off, step 1, force diagram. And so based on the picture given, it's on the right-hand side of this horizontal elliptical circle, right? And so we've got weight, and tension is pulling at an angle. Now it's going to be the hypotenuse, so tension is going to be bigger. How do I know it's the hypotenuse? Well, we just said the vertical component of tension equals the weight. And so again, AP doesn't want it on official diagrams, but the Y component is going to be balancing gravity. And so we can actually write our first statement, and we can say FG equals FTY. Want to do one more thing with the vertical before I leave it. What if we wanted to put that Y component in terms of theta, in terms of the hypotenuse? Notice the Y component is adjacent to that vertical angle. And so we would say FG, or MG actually, is equal to the hypotenuse times which function? If it's adjacent, cosine. And I'm going to highlight this, not so you can memorize it, but I will say tetherball and these type examples, some of the swings at Six Flags that are acting like this, it's very, very common to use this expression. Now, where did it come from? Force diagram, kind of an F-net statement. We looked at a balance statement. Well, let's keep it going. What about the X direction? Does anyone balance the horizontal component? No. So if there's nothing to balance, we got a net force. And it's moving in a horizontal circle. And so it's going to be a horizontal net centripetal force. And so FTX, F net equals MAC. And can we write the FTX in terms of theta and the hypotenuse? Notice the X component is opposite. And so we'll say FT times sine theta. And again, not that it's an absolute, but this is another common starter equation, if you will, for tetherball type problems, okay? Have we done anything new? Not really. The only thing different from this and maybe lady getting pulled by a helicopter is that little subscript C, okay? That's the only difference. We're not going to use old school kinematics to find the acceleration. We're going to use circular centripetal acceleration. And so those two, with those in mind, tension force. Now we know the mass and we know the angle. I'm going to use the vertical statement to find the tension force. Now, does that mean every single time I use the vertical statement to find the tension force? What if tomorrow they don't give you the mass? Are you going to be able to do it? No, right? And so just look at what you know and what you're given. And so mg equals ft cosine theta. Solve it for ft by dividing both sides by cosine theta. Plug in what you know. They said the mass is 4 kilograms. I'm going to use 10. Somebody be calculator ready. Divided by cosine 30. Now, as you calculate, remember we said the weight, 40, is the vertical component. We're solving for the hypotenuse. It should be bigger than 40. So just to get an idea, oh yeah, make sure you're in degree mode. Degree, degree, degree. And what do we get? Sorry, how much? I think you're in radian mode. 200 is way bigger. 46 point something, yeah. So 46.2, I think. Yeah. And the SI unit for tension? Newtons. And then B and C we'll do real quick. Angular speed, linear speed. Linear speed is actually easier to solve for first. And so if you remember the horizontal statement was MAC, I'm going to go MV squared over R equals FT sine theta. And for time's sake, I'm going to go straight for numbers. Mass is 4 times V squared. Radius. The length of the string is 2 meters. Is that going to be the radius of the circle? Go back to that original picture. Length is it's the part of the conical, right? R is going to be right here in purple. And so we get another little expression. This is when R and L don't equal. R would be equal to your hypotenuse, L, times which function? Sine. And so we actually have to do a little math. And so 2 is the length. Sine 30, thank you very much. Sine 30 is 1/2. Half of 2 is 1. Everybody understand why they're not the same? Tetherball, not the same. So now I can go down and plug in the R of 1. And now we know the tension, 46.2 times sine 30, which again is 1/2. So speedy quick. Actually, I think I remember this one. Someone can tell me right or wrong, but I think it's 2.4. Okay, so let me know if I'm right or wrong. Okay, thumbs up, good. So we get a linear speed of 2.4 meters per second. Now, how do we find angular speed? Well, the new equation, if you'll embrace it, V equals omega R. The workaround is you would use circumference over period to find the period, and then use the period to find the angular speed, or put those two equations together and use this one. And as it turns out, so angular velocity would be V over R. And just because the radius is 1, you get 2.4 again. But let's take a closer look at units. 2.4 meters per second divided by 1 meter. What's the unit for angular speed? Something over seconds. And this is kind of weird. True story, y'all, true story. You can say 1 over second, but that's weird. We're not used to that. Or you can say placeholder radians per second. Okay? In terms of saying something, radians per second. It's not really a unit, but it's a placeholder. Good deal? And now put a pig on that string. That's your lab when pigs fly. It's going to fly at an angle, so it's going to be like this tetherball. So we'll probably start next class doing the one below. It's got some concepts with it and one new term, frequency. Don't worry, it's not bad. Y'all have a great weekend. Make sure you're semester reviewing and independent practicing. Okay. And I'll see y'all Tuesday.